Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is gas mixture UH and S properties, and the section in the textbook is 13.3. So here are the learning outcomes. At the end of this video, you'll know how to calculate values for U, H, and S for ideal gas mixtures, and you'll know how to calculate the same properties, UH and S, for non-ideal gas mixtures. And you'll be able to apply the compressibility departure charts to a gas mixture for an energy balance. All right, so first I want to kind of talk about gas mixtures and what we're trying to do here. And so remember, we've got here I have a binary mixture of gases, two gases. I've got a blue one and the red one. And what we're trying to determine now are these properties U, H, and S. In a previous video, we looked at PV and T properties, but now we're looking at these internal energy, enthalpy, and entropy values. And it's actually pretty straightforward. The total internal energy of a mixture, which I'm denoting as capital U sub m, that's an extensive internal energy. We just sum up all the energy of all the red molecules and all the energy of the blue. And I can break that down into the mass of the red particles times their specific internal energy. So this is the energy per mass. And then I'm just going to go ahead and add the blue. And I can do that for each constituent that I have. Right? If I want to know the change that's going on, so whether this is going through a process, the change in internal energy of the mixture, well, again, if this is a closed system, for example, I will just take the mass of the red, and I'll look at what the change in internal energy is of the red, and then I'll add it to multiplying the mass of the blue times the change in energy of the blue. So I'm just kind of taking each component individually and looking at their changes. I can do the same things for delta H and delta S, and so just kind of wrote it down here fairly quickly. But again, what we're doing each time is we're just going to go ahead and multiply the mass of each particle, each constituent, times its respective change. Sometimes it's a little easier to express this in terms of moles. So instead of given the mass of each constituent, you might be told what the number of moles is. It's pretty common. And so the only change is now we would be using the number of moles, which the symbol we use is capital N. And so then when our change in internal energy or enthalpy or entropy, there's this over bar usually to denote that this is going to be per mole. So we're just going to be finding this in terms of per mole instead of per mass. And sometimes it's a little easier. It just depends on what information you know in the particular problem. Now I want to talk about another approach that you can do, and this is kind of the idea of using average properties. And so, so imagine now I've got, again, a gas mixture, but now I have this really diverse mixture. I've got 4 different gases in here now. I've got red, blue, green, and purple. And maybe it's going through this compressor and coming out on the other side. Now, as we just said, so if I want to know the change in enthalpy, total change in enthalpy of the mixture, I would end up just summing the mass of each constituent times the enthalpy of each constituent. And let's say maybe what I want to know here is what's the power requirement of this compressor. So if I did the energy balance for that, the power requirement of that is going to be, well, what I would need to do is going to have to sum up the mass of each constituent times the change in enthalpy of each constituent. That would be the mass flow rate of each. Now I've got 4 gases, and so now I'm going to have 4 different terms in here, and you can imagine this gets to be a whole lot of terms, and a lot of the terms are going to be the same, particularly in terms of the delta T. And so this is the idea of just defining an average property. So remember, the enthalpy, we can write the enthalpy, for example, of an ideal gas is just the heat capacity times the temperature. And so what it might be easier is to find a mixture C sub P, so I'll call it a C sub P of the mixture. And then what I'm going to do is I'm just going to find the average. And so what I'm going to do is I'm going to sum up, for example, the mass fraction of each constituent times the CP of each constituent. So I'm just weighting each one of the blue, the green, the purple, the red, to give myself a value of C sub P. And then I could go ahead and put that in and now say, okay, well, delta, for example, the work requirement is going to end up being equal to the mass flow rates, the C sub P of the mixture times delta T. And then what I would end up doing is just taking the total mass flow rate of this mixture. So this now is the total mass flow rate going in, not the mass flow rate of each individual component. Now I want to talk about some things I can do if I've got an ideal gas. So far we haven't been talking about whether they're ideal or non-ideal. And the idea of this is what's known as the Gibbs-Dalton law. And the Gibbs-Dalton law is an extension of Dalton's law, which said particles are going to act like they are alone at their own pressure, and so I would be kind of breaking each one by itself. So the idea here is that the purple is going to be acting like it was just out in its own world over here, not seeing any of the other molecules, the red ones as well. And so they're all acting at essentially lower partial pressures of each. And that's okay if it's an ideal gas, because ideal gases don't see each other anyway. So the purple ones, if they were just looking at the purple molecules or looking at the purple molecules in this mixture, since they don't see each other anyway, that would be fine. So that's how we can apply Gibbs-Dalton. And so remember, for Gibbs-Dalton, the enthalpy is just a function of temperature. For example, enthalpy is CPT, and so obviously this change in pressure is irrelevant for the enthalpy values anyway, because it was never a function of pressure. Now, it's a little different if I look at entropy, and so here's the equation for entropy. So if I wanted to know what the change in entropy is, and we're going to sum up the changes of each of them, and so here I would be taking the mass fractions, and now I've got the delta S for an ideal gas. So this is Cp, I want to T2 to T1, so maybe an inlet and an outlet, or an initial conditions and final conditions. But one of the things I want to point out are these pressures over here. Note that these pressures over here are partial pressures. So for example, that would be P sub I of the purple. And for an ideal gas, that's going to be Y sub I P of the mixture. And so each one of these pressures down here should be Y sub I P of the mixture 2, and this would be Y sub I P of the mixture 1. All right, so they're actually smaller values. Now, in this case, for ideal gases, those are going to cancel and you end up with the same value. But what we'll find out is that if we have a reaction going on, or if maybe some things are mixing such that these mole fractions change from the initial state to the final state, that's not necessarily going to be true. And we're going to see that in some later videos, and we'll also see it in later chapters. So it's an important point to keep in mind. All right, so let's go ahead and just do an example first with an ideal gas. And so here's the problem we've got. We have a 50-50 molar mixture of helium and ethane, and it's compressed from these conditions of 15 psia and 60 degrees Fahrenheit to 100 psia isentropically. And we want to find out what the final temperature is. And so we're going to go ahead and assume that this is an ideal gas mixture. And so we can go ahead and determine what this is. And so what we're going to have is we're going to have delta S, and that's going to be equal to 0 because it's isentropic. And what that right there is going to end up being equal to is a summation of delta S of each of the individual components. In this case, it will be the helium and the ethane. And since I've got this on a molar basis over here, what I could do is I could go ahead and change it into mass fractions. And so this would end up being summation of the mass fraction of each times S sub I. All right? So this is an extensive entropy here that I'm looking at. This is an intensive entropy here. So first I need to go ahead and determine what the mass fractions are. And so the molecular weight of ethane, I'll write it MW sub E. Ethane has 2 carbons and it has 6 hydrogens, so its molecular weight is about 30. And the molecular weight of helium, I'll write it, MW. Molecular weight of helium is 4. And so if I want to look at what the mass fractions are, the mass fraction of ethane is going to be 30 over 34, and the mass fraction of the helium is going to end up being equal to 4 over 34. And so this value right here is 0.88, and this value right over here is 0.12. And just to double check, my mass fractions always need to add up to 1. So now let's go ahead and do our isentropic relation, saying that delta S, which is equal to 0, is, I'm going to take my mass fraction, so this is supposed to be ethane 0.88. And so the equation that I'm going to be using, so it's right over here, delta S is equal to Cp natural log of P2 over T1 minus R ln of P2 over P1. I'm applying that for each one of these, and so now the Cp of ethane is 0.427 natural log of T2 over my initial temperature, which is 60. I need to do that in absolute, so it's going to be 520. And then I'm going to have minus 0.06616 natural log of 100 over 15. All right, so that right there is my ethane term. And now I need to go ahead and add that to the other one. Let me go ahead and erase that equation now that you know which one that we're using. Well, actually, it looks like my pen's not able to erase that. So I'll just go ahead and scratch that out for here. So I'll lay it down here. I got room 0.12 and heat capacity 1.25. Natural log of T2 over 520. And then my R value here for hydrogen is 0.4961 out of 100 over 15. And so now I can go ahead and just solve that equation there for T2, probably a little easier in an equation solver, but for your calculator, if it's programmable. T2 is about 795 Rankine, and that's about 335 degrees Fahrenheit. So it changes about 300 degrees. So maybe my assumption of a constant heat capacity wasn't entirely correct, but at least it kind of shows you how you can go ahead and do this for gas mixtures that are ideal. All right. So the next thing I want to discuss is what to do if it's not ideal. So now again, I'm looking for my properties U, H, and S, but I want to know what I'm going to do if this is not ideal. And so a couple different ways I can do it. If I want to use the departure charts, remember, for example, the enthalpy, we have this enthalpy departure term, C sub H. So we would just find the ideal enthalpy, and then we subtract it off this term. If I want to know my changes in enthalpy, well, I would just have my changes, assuming it's an ideal material, and then I'm going to subtract off this secondary departure term right there. So pretty straightforward. So what I'm going to do now, if I have a gas mixture, if I want to know my change in enthalpy, well, I'm just going to be taking each of the mass fractions by their respective change. And so this value is going to go in there. So effectively this whole thing right there is going to go in there for each of my constituents. And so I'm going to have a value of ZH2 and ZH1 for each component. So if I have two components, in each one I'm going to have to look up two values of the enthalpy departure. I'd end up having 4 enthalpy departure terms. Right? I can do the exact same thing for internal energies and entropies, where again I'll just be using departure term, adding something to the departure term each time. All right, so let's go ahead and look at an example, and here I'll do an unsteady example. And so what I have is this mixture of 3 kilomoles of hydrogen and 0.75 kilomoles of nitrogen, initially at 160 Kelvin and 5 megapascals. And then it's going to be heated at a constant pressure up to 200. So the pressure is going to remain constant. I want to know how much heat was added. And so I'm looking for what amount of heat is that goes in. And so if I write my energy balance for this, right, we know that the heat that goes in minus the boundary work is going to be equal to the change in internal energy of the mixture. And since this is constant pressure, I can move my boundary work term into here. And then I know Q is going to be equal to delta H of the mixture. So that's what I'm going to be looking for. And what I'm doing now is I've got effectively a non-ideal gas, so I'm not going to assume it's ideal. And so what I'm going to do in order to find Q is I'm going to be finding Q assuming it's ideal, and then adding Q, which is a departure term. Right? So I'm going to be finding delta H ideal plus delta H departure. Right? So there's the way that we're going to go ahead and approach that. And so first what we can do is find Q of the ideal, and that right there, Q ideal, you can just have as Cp delta T, and what I can do is go ahead and calculate either an average Cp or I can weight each one. And so what I'll do is I'll go ahead and weight each one since I've got an extensive amount. And so I'll have my 3 kilomoles, so that's of my hydrogen. Its Cp, I'll use values at 300, so that's about 28.6 just because I've got that in the table. And then I'm going to go ahead and add my 0.75 for the nitrogen and its Cp, which is 29.09. And then I'm going to multiply both of those by my delta T. It's going from 160 to 200, so that's times 40 Kelvin right there. And that value ends up being equal to 4305 kilojoules. So there's my ideal. And now I need to know the departure terms, which means what I need to do is determine reduced temperatures and pressures of each of those. And so the reduced temperature, remember reduced temperature is T over T critical. And so if I do this first for hydrogen, I have 160 over 33.3, and that's equal to 4.8. And if I do TR for the final state is 200 over 33.346. And the reduced pressure, which is constant for this whole thing, is going to be 5 megapascals over 1.3. And so that right there, my reduced pressure is 3.85, and that remains constant. So this is TR2, this is TR1, and both of those are for hydrogen. And if I do the same thing for nitrogen, I'll go ahead and just skip the intermediate steps on there. TR is 1.27, that's the initial one for nitrogen, and the final state for nitrogen is 1.58, and its reduced pressure is 1.47. All right, so here I've got my initial and my final reduced temperatures and pressures for each of the constituents, and what I need to do now is go ahead and look up my departure terms for each one and put that in. And so I'm going to have one final equation. I'll kind of put it down here at the end because I'm running out of room here. First, I've got my ideal term, which I had is 43.05. And now what I'm going to do is I'm going to add the departure term, and actually it's the way it's written is with the minus sign. So it's going to be minus the number of moles, which would be 3. Since I'm doing this in moles, I can do 8.314. which is the ideal gas constant. The critical value, and this is hydrogen, so it's 33.3. And then what I need to do is look up my value of Z sub H, and I've done that, and it's actually minus 0.3 at the final state, and then it's a minus 0.193. Actually, a couple negative values because it's the high reduced pressure over here. Well, actually, it's really because it's at a high reduced temperature. But if you just go ahead and I plug those into EES. And then what I need to do is go ahead and add my other term, which is actually going to be subtracting, because again, we're subtracting RT critical and then the ZH values. And so that would be 0.75 for my nitrogen. I can again use 8.314 because I'm doing this in moles. The critical is 126.2. That's in Kelvin. And the departure terms are 0.694. Again, I use DES to find the 1.196. That's why I have so many significant figures. And if I go ahead and do that arithmetic, I get 4789 kilojoules. And so we start off, the ideal component was 43. We add another 400. It's about a 10% change in the whole thing. So, all right. So that's how you do it if you have non-ideal and using the departure terms.